In this mini lecture, we are going to talk about batteries. We've been using batteries for a while, but we're just going to talk a little bit more about them. So there are many types of voltage sources. These devices supply current if connected to a resistance. On the small scale, the potential difference between one end of the battery to the other creates an electric field that exerts force on charges, causing current. So we call this special type of potential difference inside a battery an electromotive force, which we abbreviate as EMF. So a lot of times you're going to see me interchange these words. I might talk about the potential of the battery. I might talk about the voltage of the battery. I might talk about the EMF for your power source. So I'm going to use all of those words interchangeably. The electromotive force just means that this is a potential difference that is supplying an electric field that exerts forces on the charges in our circuit, causing those electrons to move around in the circuit to create a current. All sources of EMF, electromotive forces, have an internal resistance in them. And for this segment, we are going to refer to the EMF. Sometimes I'll use this fancy script E here to refer to the EMF, and it has units of potential. And we're going to talk about the internal resistance of these EMF sources, and that's little r. Now, these quantities are fairly small compared to the, resistances that we've been using in lab. So in reality, the voltage output measured across a battery, terminals, for example, is called the terminal voltage. So the terminal voltage is always a little bit smaller than the EMF supplied by the battery because the voltage source has some internal resistance. So actually, to calculate the terminal voltage of a battery, the terminal voltage is equal to the EMF supplied by the battery minus the current running through it times the little r, the little resistance, the small amount of internal resistance in your battery, let's say. The EMF is kind of the ideal potential that can be supplied by your battery, but the terminal voltage is always going to be a little bit less because that is also impacted by the internal resistance. Our terminal voltage, if I took the voltmeter between the ends of my batteries here, that terminal voltage will equal the ideal EMF that this battery could supply minus the current running through it times the internal resistance of this battery. We can place batteries in series and in parallel in order to supply current to a system. So here we have two voltage sources that are in series. And when our voltage sources are in series, the sum of their potentials add. And so then if each one of these batteries had a potential of 1.5 volts, we sum up those potentials since these batteries are in series, and then the total EMF that is supplied to this circuit is 1.5 volts plus 1.5 volts equals 3 volts. Now, in order to find the current within this circuit, we have to use, our equation for Ohm's law. V is equal to IR. We solve it for I. So the total current in our circuit is equal to the potential divided by the resistance. So the potential in this circuit is going to be the sum of the EMFs supplied by my two batteries because they're in series. And then I have to divide it by the total resistance in the circuit. Now we've got the resistance of some light bulb or some device that we're connecting in series with these batteries. And these batteries are in series with this particular resistor here. So the total resistance in this circuit is just going to be the sum of the internal resistances of each of those batteries plus the resistance of the device that I've connected in series to these batteries. So you could find the total current in this circuit with this particular equation right here. So take a look at it and ask yourself, does that make sense? How did we derive it? And I just explained it here, but I didn't write it down on the board. So think about how we could go from this circuit here to this equation for finding the total current in the circuit. Now, here we have two voltage sources that are in parallel with each other. Now, the interesting thing when we have these batteries in parallel, their potentials, their EMFs, do not add. Since these are in parallel, we'll assume these batteries are identical. Let's say they both have an EMF of 1.5 volts, EMF of 1.5 volts, EMF of 1.5 volts. If they're in parallel with each other, they are only supplying an EMF of 1.5 volts to this resistor. So no matter how many batteries I want to put in parallel, if they're all identical, I can put 1,000,000 of these batteries in parallel with each other, and if they all have an EMF of 1.5 volts, I'm still only applying 1.5 volts to my of EMF to my resistor here. This is some device that I'm placing here in the circuit that's being supplied with potential from these batteries. Now, because all of these batteries are in parallel with each other, their internal resistances are going to add in the same way that resistances add when we are in parallel. So you've got the inverse relationship for how resistors add in parallel. And then all of these resistors are in parallel with each other, which are then in series with the load. They're in series with whatever device I'm trying to send current through. So then we can figure out what the current is in this particular circuit right here. So this is the equation for the current within this circuit if we have two identical batteries in parallel supplying a current to this load. And we're going to walk through how we can get this equation in particular. It's a little bit more complicated than getting this one over here for our batteries in series. And then we're also going to apply that idea to solve a problem.
We're going to solve a problem where we've got two batteries in parallel with each other. Two batteries here, these are my batteries, with identical EMFs of 12 volts are placed in parallel, and they supply a potential difference to a device with a resistance of 100 ohms. The internal resistance of each one of these batteries is 0.5 ohms. What current flows through our device here with a resistance of 100 ohms? Okay, so in order to solve this problem, we've got to think about a couple of things. When batteries are in parallel, their EMFs do not add. So when we put a whole bunch of identical batteries in parallel, they're still only supplying the same amount of EMF to that entire circuit. So even though we've got two batteries in parallel, they both have an EMF of 12 volts, so our total potential in the circuit is also just 12 volts. Then to find the total current in our circuit, we can use Ohm's law, V is equal to IR, and we can solve it for the current. So the current is going to be my total potential, which is 12 volts, divided by the total resistance of this circuit. So the total resistance of this circuit is going to involve the resistance of this device that I'm trying to power, and the resistance, the internal resistance of my two batteries here in parallel. So we already know this is 12 volts here. We have to find the total resistance of this circuit, which combines this resistor and it combines the internal resistance of these two batteries in parallel. Since these batteries are in parallel, then we can find the equivalent resistance for these two resistors in parallel. So 1 over the total internal resistance for these batteries in parallel equals 1 over the internal resistance of the first battery plus 1 over the internal resistance of the second battery. Since these are in parallel, we can use our rules for resistors in parallel. Okay, so we take the inverse of both sides. Our total is equal to 1 over the internal resistance of the first battery plus 1 over the internal resistance of the second battery and we take the inverse of that, or we can raise it to the power of -1. And I'm just going to leave it right now in the equation form like this before I plug in any numbers. Now, since these resistors were in parallel, right, we just found the total internal resistance for these two batteries in parallel. So these batteries in parallel are in series with our device right here. So when we're in series, the resistance adds. Our total resistance for this entire circuit then will be the internal resistance for these two batteries in parallel, which was our total, little r total, that's our total internal resistance of our batteries in parallel, plus the resistance here of our device that we're trying to power. Okay, so the total resistance of this circuit involves the resistance of this device here plus the resistance of these two batteries in parallel, plus the internal resistance of these two batteries in parallel. And since these two in combination are in series with this one right here, we can add these two quantities up to give us the total resistance of this circuit. And if we write this out in our equation form, our total resistance is 1 over R1, little r1, plus 1 over little r2, 1 and 2, okay, to the -1 plus R load. Okay, so then I can take my equation for the total current in this circuit. My total current is equal to my total voltage over the total resistance in this circuit, and that will equal, we'll still keep it as V total, all divided by, we've got this 1 over R1 plus 1 over R2, all to the -1, the inverse of that, plus the resistance of our 100 ohm device. Then our total current is 12 volts divided by the internal resistance, 1 over the internal resistance of our batteries, plus 1 over the internal resistance of the other battery, all raised to the -1 plus our 100 ohms right here. So whenever I take this quantity right here, 1 divided by 0.5 ohms plus 1 divided by 0.5 ohms, and take the inverse of that, this piece right here is 0.25 ohms. Okay, so my current then is equal to 12 volts divided by 100.25 ohms. I've got my 100 ohms coming from this device I'm trying to power here, plus the 0.25 ohms, which is the total resistance, the total internal resistance of my batteries in parallel here. So I take 12 volts divided by 10.25 ohms, and that gives me a total current in my circuit of 0.1197 amperes. Okay, so in lab, we are dealing with batteries that are not ideal. We have batteries that have some amount of internal resistance within them. So that means whenever we're building our circuit, we're not always going to get, and probably never going to get, the theoretical value for the current that we should get if we assume an ideal battery, because all these batteries have some small level of internal resistance.
What I've done here is taken two circuits. Both of my circuits have a resistor of 10 ohms. This circuit on the right has one 9-volt battery. And this circuit on the left has two 9-volt batteries in parallel. And these 9-volt batteries in parallel, they're connected in parallel to each other. And then they're supplying potential or EMF to this resistor over here. Now, in both of these situations, so I've got my ammeter out and I'm taking a measurement of the total current. In both of these situations, the total current in my circuit is the same. It's 0.9 amperes. When we have batteries in parallel, those potentials or those EMFs do not add together. Instead, if they're both in parallel, these batteries are both in parallel with each other, no matter how many I add in parallel with each other, they're still only supplying an EMF to this resistance of 9 volts, the same EMF as their individual potentials. And so in both cases, we have 0.9 amperes of current in the circuit. But let's see what happens when I increase the internal resistance of these batteries. Right now, they have 0 internal resistance, so we're assuming they're ideal batteries. And I'm going to increase the internal resistance of all these batteries to 1 ohm. And when we do that, we see that this circuit on the right, its current immediately decreases to 0.82 amperes. But this circuit over here on the left, the current running through it, the total current, is only 0.86 amperes. So when we've got these batteries in parallel, the total current being supplied, if they have some internal resistance, is going to be greater than the total current that's being supplied by this battery on its own if it has some internal EMF.